friends, I'm once more back again with continuation of our other video on superposition of waves. In this video we'll take care of group and phase velocity and try to find out the relation between them and their respective expressions. Already have discussed something about phase velocity in a nutshell, and here we'll see how their conceptions have been cleared while discussing the superposition of waves. So let's proceed. The first thing that strikes in our mind is that if you say that there is a matter wave, and what kind of wave is this? It means is it a single monochromatic train of waves, or an infinite series of waves, or simply a group of waves, just like the properties of dispersions where we have group of waves and spreading over a finite region. So the representation of matter wave is a very important thing, and question in front of us is that whether we'll take a infinite series of waves, monochromatic series of waves, or a group of waves having different velocities. So for that we consider equation 1 as shown here, where psi naught is the amplitude, and this equation represents an infinite wave of same amplitude. That means the waves are of same amplitude, as well as we have a large number of waves having the same velocity here. So the velocity here can be said to be as phase velocities, and it is given by this Vp equal to lambda nu as usual. And as we have already found that Vp is equal to c squared by v, the relation between material particle velocity and phase velocity, and also the de Broglie wavelength, that is the de Broglie relation, lambda equal to h by mv. These 2 and 3 are already we have discussed in our earlier videos, and with this we see that if we consider infinite train of waves, then we all of having the same amplitude, then we have a velocity for all the waves same velocity, and that is phase velocity, and it will be given by equation 2 as shown here. Now if you look at equation 2, since b is the material particle velocity and b is always less than c, that means that Vp is greater than c. So this fact is here, v less than c, that means Vp is greater than c. So the meaning of this is that if we represent the material particle by a wave, that's a matter wave, then the matter wave will move at a faster rate than the particle. That means the particle will leave behind, while the wave representing it would be moving far away because it has a velocity greater than c. This definitely says that we cannot take the phase velocity as the velocity that a material particle would represent, as we have seen here. So our conception of infinite number of waves having the same frequency, same amplitude goes away, and we now have a group of waves having different velocities, or the group of waves moving with an average velocity, which will be later termed as group velocity. So regarding this situation where a material particle moving with a phase velocity means that we have an infinite number of waves all having same velocities, that is the phase velocity, and also that they are having same amplitude, meaning that there is no dispersion, because dispersion means velocity is dependent on frequency or wavelength. And thus if we take the case of single monochromatic train of waves or infinite number of waves having same velocity, then it will mean that we have no dispersion for matter waves. But in reality, the matter wave shows dispersion, and the phase velocity actually depends on wavelengths. And this means that we need to think of a group of waves all having different velocities, different phase velocities rather. But the amplitude of all the group of waves would have a common velocity, or a average velocity, which will be known as group velocities. So to conclude that we cannot represent a material particle or a matter wave by a single train of monochromatic waves, but which is moving with a phase velocity, the same velocity, Rather, we will take care of the fact that they move with different phase velocities, but their amplitude is moving with a common average velocity, known as group velocity. So the conception of infinite train of single monochromatic wave goes, and we see that a wave group is to be wished to represent a material particle, and this wave group will be known as wave packet, and thus the average velocity of the group of wave will be the material particle velocity. Precisely speaking, the concept of individual waves is incomplete because it corresponds to phase velocity and no dispersion. But in reality, for matter waves, dispersion occurs, and that's why we have to take a group of waves, all of them having with different phase velocities, but their amplitude moving with a common velocity. And thus the physical situation can be represented in an effective way. And this particular figure shows us a wave packet where the envelope represents the amplitude, and this carrier is related with phase velocity, and the amplitude is moving with a particular velocity, that is the average velocity known as group velocity. And also we must take account of the fact that since there is a finite spread of the wave packet, so there is no precise location of the particle here, and when we do a measurement, we always take the position as the position of maximum probability. And that means that once we do an experiment and we find a particle, and we say that this is the position of maximum probability. And these kind of things will be later discussed more while discussing about Heisenberg uncertainty principle from the wave packet point of view. So let's now find an expression for wave velocity and group velocity. For that, we consider only two waves which is forming a wave packet, and one wave is represented by like this, and the second wave is represented like this. The amplitude of both the waves are taken to be same, but their wave frequencies are different by d omega, and the wave number is different by dk. And the resultant wave that is representing the wave packet is now given by this, as given by equation 4. So I'm doing some simplifications, just like sine A plus sine B equal to twice sine half of A plus B into cos A minus B. This kind of relation are used while getting this equation 4. So since this omega is very greater than the difference between the two waves, similarly wave number k is very greater than dk, that is the difference in wave number. So 4 becomes this, neglecting these two terms d omega and dk here in 4. So we have now expression 5. In expression 5, we see that it's a resultant wave due to the superposition of the two waves, and they are moving with angular frequency omega and a wave number k, and thus this particular factor, sine factor, is representing the phase of the particle, and this will be responsible for their phase. But while this particular thing, twice sine naught cos, and this particular thing square bracket d omega by 2 t minus dk by 2x, this represents the amplitude of the resultant wave, and this amplitude is moving with an average velocity, and we'll see that this average velocity is the wave group velocity, and we can find an expression for it. Now coming back to equation 5, the phase velocities can be easily defined because this is related with phase factor, and so phase velocity is omega by k from the sine term, and the group velocity is from this cosine term representing the amplitude. So group velocity is d omega by dk, and while phase velocity is omega by k as given by equation 6. So we can now find how this group velocity is related to material particle velocity v. For that, we take the relativistic expression for omega. This is twice pi nu. Nu is, since each nu represents the energy, and is equal to gamma mc square. So h nu equal to gamma mc square. That means nu is equal to gamma mc square by h. So that's why omega is equal to twice pi gamma mc square by h. And since gamma is equal to 1 by square root of 1 minus b square by c, so ultimately omega is given by equation 8. Similarly, wave number for the relativistic case is twice pi by lambda. Since you know that lambda equal to h by gamma mb, where gamma mb represents relativistic momentum. So putting it here, and again gamma is equal to square root of 1 minus b square by c square, so that's why k is given by equation 9. Now these equations simply represents the fact that both omega, that's wave frequency, and that wave number are function of material particle velocity. Now the group velocity, as we know that d omega by dk, we rewrite it like this: d omega by dv divided by dk by dv, as in equation 10. And from it we know that d omega by dv, after doing all the differentiation, twice pi mv h or 1 minus b square by c square to the power 3 by 2 as given by equation 11. And then dk by dv from expression 9 we get like this after differentiation of it, leads to twice pi m h divided by h 1 minus b square by c square to the power 3 by 2 as given by 12. So we got d omega by dv from 11 and dk by dv from 12, and putting this 11 and 12 back in 10, we get v is equal to b. That means the group velocity is equal to material particle velocity. We can conclude now that our conception that the amplitude of the group of waves moves with a average velocity, and which is known as group velocity, and correctly it is representing the material particle velocity also. And this fact saves us from the devastating situation while finding that the matter wave representing the particle is moving at a faster rate than the particle itself, leaving it behind. So this fact, this particular devastating situation is removed here, as we get the v is equal to b here. And also we say that from 8 and 9 here, from 8 and 9 we divided omega by k, will find that omega by k is nothing, it is simply vp. So vp equal to c square by b, which is already we have written earlier, and also we got it in our earlier videos also. Also we can show that vp is equal to vg minus lambda dv by d lambda. This particular equation 14 represents the fact that the wave packet or the matter wave suffers dispersion, and that's why phase velocity is not equal to group velocity. For example, if for electromagnetic wave in vacuum, just like light, it has no dispersion, that is the phase velocity does not depend on wavelength, and in that case then vp is equal to vg. But for matter waves they are not equal, and so this equation 14 represents correctly the fact that dispersion occurs in matter waves, and we cannot have a phase velocity equal to group velocity. But if this part disappears, that is which represents the dispersion part, then definitely phase velocity will be equal to group velocity, and this kind of situation can be found if for particular situations. So conclusion is that you cannot represent a material particle by a single monochromatic train of wave, infinite number of waves having same frequencies and same velocities, same phase velocity, but rather we talk about group of waves, all of them having different phase velocities, so that their amplitude move with a common velocity or an average velocity, and this common and average velocity is known as group velocity. And we can prove that this group velocity for a matter wave is same as the material particle velocity, and thus effectively showing that the material particle can be represented by matter wave. So lastly we have some assessment here. What do you mean by the linearity and superposition principle in quantum mechanics? This is discussed in our last video. Explained the two-slit experiment with electrons with the help of superposition principle. In the last video we showed how the superposition principle can be understood in terms of two-slit electrons. We saw here that the classical kind of things that cannot happen in case of two-slit experiment with electrons while discussing this superposition principle from the Schrödinger equation. What is phase and group velocity? We know phase velocity is the velocity with which the phase of the wave moves, and group velocity means the average velocity of the waves with which the amplitude of the wave moves. Find the relation between them, already you have done it. And then why is the concept of wave packet necessary in quantum mechanics? Because a single monochromatic train of wave cannot represent a material particle. That's why you need a group of waves or a wave packet, and then so that group velocity is equal to particle velocity. This is also done here already. So with all this, I'm ending up this video. Hope that this video is useful for you. Thank you very much for watching our videos. Keep commenting. Thanks once more.